Hello everyone, I am Felipe Carvalho. I am a PhD student in mechanical engineering at the University of Campinas. I will present some development of my PhD project and the development of Thiago's research. We are advised by Professor Alberto Luiz Serpa. Our topic here is the modeling and simulation of electrical submersible pump dynamics using transfer functions and bond graphs. I'm going to cover the general motivation of our research. Next, I'm going to introduce and present the bond graph modeling and results, which are my research. Then, I present the transfer function modeling process and present some simulation results, which are the Thiago research. Our main motivation is that during the artificial lift process, the electrical submersible pumps, or ESP, may face multi-phase flow scenarios. In this context, one possible multi-phase flow scenario is a liquid-liquid two-phase flow, which is composed by two immiscible liquids, such as oil and water. The motion affects negatively the ESP by changing the fluid effective viscosity. Also, the motion are subjected to phase inversion problems, which cause an abrupt change on the fluid viscosity. These effects cause ESP instabilities, which are a dynamic behavior. Here, in this figure from Pass and others' work, we have the ESP dynamic behavior due to the motion formation and the actual production. You can observe that the discharge, intake, and motor temperature and motor current are oscillating along the time. According to Pass and others, these instabilities affect the surface flow rates, ESP current, temperature, pressures, and can lead to mechanical failures. In the Pass and others' work, they mentioned that one of the methods to stabilize the ESP operation is the emotion brake injection. You can see in this figure that the ESP parameters are oscillating, then the motion breaker is injected, then the ESP parameters stabilizes. However, one of the alternatives to stabilize the ESP is by changing the operational point, which can be made by using an automatic control. Usually, they require a dynamic model to be tuned. Thus, one of the main objectives is to devise a dynamic model to improve the understanding of unstable pump operation under liquid-liquid flows and multiple ESP systems. This dynamic model can be useful for developing automatic control, strategies, decision-making, and obtaining a digital twin. Now, moving on to the ESP modeling using bond graphs. The bond graph is a technique used to model multiphase dynamic systems. One of its characteristics is that it uses the same visual representation for different physical domains. Here, as an example, we have the bond graph for a DC motor coupled with an axis. The same model can be observed here in this figure, where we observe the electrical domain inside this blue square and the mechanical domain inside this red square. Here both in this is the system and the bond graph. Then, using the bond graph technique to model the ESP impeller, we have this bond graph model here proposed by the Tanaka and others. It has coupling between the ESP and the upstream pipeline and the downstream pipeline. In this model, we can observe the leakage loss, shock loss, friction loss, diffusion loss, and shock loss at the impeller outlet, and the liquid inertia as well. From the bond graph model presented previously, we can obtain a differential equation for the ESP impeller. Here, we have a differential equation without the leakage loss, using the bond graph technique. From the literature, we have the Kulik and Haeckel model here in this differential equation here, where the authors obtained analytically the dynamical model for the impeller using the conservation of momentum and mass. The equations here appear different, however, they are the same equations, but written differently. Here, in this equation, we have the relationship between the parameters, where we have the impeller geometry parameters, impeller friction, impeller inertia, and input torque. Now moving to Thiago's research. Another approach to obtain the dynamic model is to use experimental data and system identification tools to obtain the transfer function of the system. This empirical approach does not physically model the system like the bone graft technique, but tries to obtain the system model by analyzing its response to some input. One widely used method for identifying dynamic systems at the industry is the reaction curve methods, such as Smith's method. With the transfer function, it's possible to simulate the ESP behavior under different conditions and inputs. Now, moving to the modeling part. The first step on using the Smith method is to determine the transfer function order. In this case, Thiago considered a first-order transfer function with a delay given by this equation here. This transfer function has three parameters that we have to obtain experimentally: the k, the theta, and tau. To apply the Smith method, it's necessary to have a system on a steady-state condition and apply a step on the system. After the system stabilization, there are 2 points of interest: the time where the system reached 28% of the amplitude of the stabilization, and the time where the system reached 63% of the system stabilization. These 2 times are used to calculate the tau and theta, and then calculate the k through these equations here. In order to evaluate the Smith technique, Thiago used the simulated gas weight fraction dynamics from Germania's work. Here, on the right, we have the gas weight fraction on the y-axis and the time on the x-axis. And we observe the gas weight fraction variation along the time when a gas valve is open and the gas is injected at the ESP upstream for different rotations. Then, Thiago applied the Smith technique and obtained the first-order transfer function for a single-stage centrifugal pump, and the results for Thiago procedure is presented here on the right, where the gas void fraction is obtained along the time using the transfer function parameters obtained with the Smith technique. Moreover, Thiago applied the same technique for different ESP rotations, and the results are presented here on the left, where you have the gas weight fraction variation along the time for different ESP rotations. Then Thiago coupled 2 single-stage centrifugal pump transfer functions to obtain the gas weight fraction dynamics for a 2-stage centrifugal pump. The results are presented here on the right. Currently, Thiago is working on applying the Smith method for obtaining the transfer function for the pressure dynamics. Finally, I would like to thank my sponsors Equinor, FAPESP, and NEP, and thank the University of Campinas, Alpha Group, Serpa, and the School of Mechanical Engineering for the support. Thank you for listening. Bye.